one of the things I hear about 3D printing quite a lot is, well, it's just a hobby. It's used to make models and toys. Why can't we make some real machines out of it? Now, 3D printing has been used to make real machines, but that was playing in my head for a bit when I came across this mechanism drawn by Thang. Thang does some awesome work, and anything that moves is always really cool. And I looked at this mechanism, and the first thing you think about when you see something like that is, well, that is awesome, but what's it used for? Now that is used for things like pipe building machines and cable wrapping machines. And there was a brilliant video of a chap who did a build out of steel of a cable tie wrapping machine, and it was just beautiful. And I thought to myself, well, can we actually do that in 3D printing and make ourselves a useful machine using 3D printing? Now, if you look at both the drawing and the machine as it was made, its key component is a ring gear, and it's an internal ring gear. Now, you can draw internal ring gears with Tinkercad, but it's a bit of a challenge and needs a fair amount of math. Much easier is just to grab one of the standard gears. Once you're in Tinkercad, go up to the search which is there and type in gear. That is what you want. It's called metric gear. Just pull one onto the workspace and you'll see it's a standard size with this pull down box. The module is the size of the teeth, so I like them nice and chunky. So if we click on there and type in 2, it will create a much chunkier tooth. And it does that by increasing the size. So you see the size there is 40, it's roughly twice the number of teeth. If we put 60 teeth in there, then we get 60 teeth. Let's change the colour of that so it's a bit easier to see. We have ourselves a massive gear. I'm going to change the size of that so it's a little slimmer, and there we go. Now we can get rid of that, take a hole, smooth it out. This, you'll note, is 123 by 123, so let's make this 110. Center them to each other by hitting the center, click to that, that centers it, and now we can merge those. We get ourselves a ring gear, but with external teeth. Now it's not too much of a problem to drive that, but it's really easy to make that. We can stick a wedge in there by pulling that primitive, changing it to a hole and reorienting it, because at the moment obviously it's in the wrong position, so we need to move that 90 degrees, check that it's on the plane, then rotate that another 90 degrees, and we can increase the size of that by pulling that bar, and we'll create ourselves a wedge. Center it to that. And we can use that primitive to chop a hole in the center so that we can actually pass the wires through. If we then merge that, we get our external ring gear with a notch cut in it. Okay, you can export that STL file, import it into a slicer and take it to your printer of choice. And once you've printed it off, that's what you get. Now you'll notice there's a couple of extra bits added here. This is going to be the tape carrier, and all it is the semicircular primitive and the cylinder primitive, so I can stick my tape on the top. Now I've chosen to make some design changes here, so we're doing it externally driven instead of internally driven, because it's easier to draw that drawing if you want to. So some of the choices I've made are just personal choices. For instance, I'm not going to use bearings. Now that will limit the life of the machine, and if you want to redesign it, you could redesign it for steel pegs and bearings if you wanted to. I've made those choices because I think I'll get enough of a life out of plastic rubbing on plastic to be able to, do a few jobs. I'm not going to use this industrially, I'm going to use it every now and then. So it's appropriate to me. If you want to make different decisions, then make different decisions when you're designing your machine. And that's what I mean about working with the tool, working with your problems, what you actually want, rather than putting up with what other people have done that you have to then put up with. You can make those changes yourself, and I'm going to make 3 changes. The externally driven ring instead of the internally driven ring is a choice I've made to make it easier to draw in Tinkercad, that's all. I could have made it internal, but I decided on external because it's super easy drawing and it doesn't really affect it. Now traditionally when you look at them you see them having a load of bearings on the outside of the ring, but here we're going to drive against the inside, and so the base unit, which is right here, it's got a whole load of support pegs to keep the top and the bottom apart, and a tiny lip in there, because this goes in there like that. And once it gets driven round, the lip holds it in place and so it doesn't slide. Of course I've got to drive it. Now you have to leave this gap so that you can get the wires in there, but it creates a problem. If you're driving by a single gear, there comes a point when the gear is in the gap and of course you lose your drive. The way to cope with that is you actually have two gears, one either side, slightly bigger than the gap. So the gear is always engaged with the drive gear and the ring gear, and of course I've created two drive gears, and those two drive gears just slot in there and there so that I get continuous drive. So there's my base plate with this little lip there. The ring gear goes on like that, and that gear goes in there, and that gear goes in there. Now when I drive that, it'll turn to that point, but then this one's also being driven so that it never loses its engagement. We obviously need a top plate on that, and the top plate equally has a little lip on it, and it fits on like that, so the whole thing's held in place. Now we need some gears on there to drive it. So we pop two gears on the top. If we drive these two gears, it will drive those gears, drive the ring. Traditionally what they do is put a chain on those because you need them to drive in the same direction. But as it happens, if you have two gears engaged, then this gear, say, is turning clockwise, this one will turn anti-clockwise. So for any two gear group, one gear turns in the opposite direction to the other gear. Of course this is true on this side as well. So if I turn this clockwise, this will turn anti-clockwise and this will turn anti-clockwise, turning in the same direction, which is exactly what we want. So if I put a support in there, which is there, pop that on, then I can engage those gears, and as I turn that one, then this whole thing will turn just exactly how I want it to. So this now becomes the main drive cog instead of having a chain, and that's the second change that I wanted to make. Because here you can make some decisions. I want to make this hand-driven because that's just my bent. I like hand-driven machines. If you wanted to make it motor-driven, that's where your motor would go. For me, I'm going to put a crank handle on it so that I'm able to crank that around. Obviously a grip handle will go on there, and then we need a couple of things here to stop everything falling off. Okay, and there's the whole thing put together. Now it's held together with super glue because in my experience, super glue is a surprisingly strong bond. In most cases, it's stronger than the plastic. But if you want different fastenings in there, well, design different fastenings. Again, it's all about choices you make. But if I turn this handle, of course, how is that turned? Big surprise. But of course it has a tape carrier there, and that tape turns with it as I crank that handle. It's awesome. Okay, there's something to notice here. That peg is on the opposite side. When I was demonstrating, the peg came up this way. But clearly that peg is for the tape carrier, and if I left it there, it would bash into the gearing. So we swap it around, and it doesn't make any difference which way around it is. So we swap it around so the peg is there, and the tape carrier will then extend over here, and as it travels up there, won't bash into the gears. And that's the tape carrier, these three parts. This bit goes on there and it's free to swivel. That's just a retaining clip to stop it falling off, so that goes on there. And then the tape will go on there like that. And this whole arm fits onto that peg there. And there you go with this tape carrier. Now it's all ready to go. The only thing really to do with it is give it a go and see. It actually worked! Amazing, hey? Like anything, it's a learning experience. I think I will put a motor on. That'll make it an awful lot easier to use, because cranking it was a tiny bit of a pain, but this bit is the heart of it, the bit that matters. And as I said, I made this size because it's the very first one I've made. I actually dreamed up this idea using those two changes, externally dribbling, and then instead of a chain, a cog there that we're actually turning. And I used a handle for it, but I think I'll put a motor on that. And of course, you can make this bigger if you want to. I just made that because it was a random guess. I've no idea how big it needs to be, but certainly that worked a treat, and I'm quite pleased about that. Now, I will put these on Thingiverse, the link will be in the description for anybody who wants this, and feel free to adapt it however you like. And we've gone through some of the ways of making it, so that if you want to make it bigger or want to make changes, then the mechanism I think is pretty clear, and what you need to do in order to get that mechanism to work to treat. I'm quite pleased with that. So a real machine made by 3D printing that can do a job. Hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.